McMurtry has been doing some very cool things lately with their Spéirling. And while there's plenty of good content out there discussing the car, I felt like there was nothing doing a really deep dive into the physics of why the fan system on this car makes it so much faster than other cars. So in this video, we're going to be looking at the fan system on the Spéirling, how it works, what compromises they had to make, and a little bit of a comparison to what you could use as alternative approaches to this fan system. For those of you that are new to my channel, I was an aerodynamicist for Mercedes for the 2018, 19, and 20 Formula 1 seasons. I now work as a consultant designing aerodynamics kits for cars in all different classes all around the world. Now, I don't want to get too much into the history of fan cars because a lot of people have discussed that elsewhere, but what I do want to do is get some broad categories set up for the different types of fan assist systems that you can see on cars. Firstly, I want to split fan systems into two main categories. One is what I'm going to call a fan assist system, and one's what I'm going to call just a straight up fan car. Now, fan assist systems use fans to enhance conventional aerodynamics, whilst fan cars, the entire purpose is to use the fan to provide pretty much all of the car's downforce. It's a subtle but important differentiation. So when I think of fan assisted cars, what I'm thinking of is things like the Gordon Murray T50, which uses a fan to suck air from the top of the diffuser to enhance the power of that diffuser, or a lot of modern Formula student cars with fans in Europe, which use fans blowing at the front of the car to enhance the power under the entire floor, get more power through that floor and through that diffuser, and that's how they generate extra downforce with those systems. We then have more of the actual fan cars, which are cars that are using the fans to create a vacuum under the car, usually by trying to seal it in, and then sucking that air out the back, usually with a set of fans, things like the Chaparral 2J, the Brabham BT50, and of course the McMurtry Spéirling. Now, these cars fundamentally rely on having a well-sealed area that seals between the car and the ground that they can suck the air out of and generate a good deal of suction at very low pressure in that region, and that's what's giving it the massively enhanced downforce. Both these types of cars use fans to assist them in terms of performance. However, there's different sets of trade-offs. The fan-assisted cars, generally speaking, will be a little bit less sensitive to car condition. We're not so reliant on a tight sealing gap between the ground and a skirt that's sealing off volume. However, they're never going to be quite as powerful as a car that's sucking fully from this enclosed space. And that's obviously the big selling point of a full fan car. So with a fan car, it's important to consider why you actually want to run a fan car versus a conventional car. Now, conventional cars with conventional aerodynamics have their downforce scale approximately equal to the velocity squared, which means in high-speed corners, you have heaps of downforce, in low-speed corners, you have less downforce. Now, downforce enhances the performance of a car by adding extra normal load to the tire, and that gives the tire essentially more grip without adding any more mass to the car. This allows you to corner harder. Now, the problem with conventional downforce is that it's a lot less effective in low-speed corners. Now, this is doubly compounded by the fact that low-speed corners are where you actually tend to spend a lot of time on track. Low and medium speed, you are in the corner for a physically longer amount of time because you're going so slowly. So if you can be a little bit faster in low-speed corners, you're generally speaking quite a lot faster around the track. So what we want to do is try and get that extra performance in low-speed corners, and we want to do that by getting more downforce in low-speed corners. So if we try to do that with conventional downforce, what we do is we increase the overall downforce in the whole car. We really crank everything up, and that gives us more downforce in the low-speed corners. The problem with that is that then on a conventional car, in the high speed, you then have a heap of downforce, too much downforce, in fact, and you can overload your tires. Now, when you do that, the tires are at risk of failure. So you can't have a car with too much downforce going on. Now, some of these issues you can solve with active aerodynamics, and we'll get into that a little bit later. But an easier and more potent way around this is to go for a fan car, a car where you're using some sort of motorized fan to blow or suck from areas of the car, and that allows you to go and get downforce as you need it on demand with the flick of a switch, because you just power up your motor and all of a sudden you have more downforce. And of course that solves your high speed issue as well, where you can just turn off the motor if you're going in a straight line. You don't need to have it going when you're going down the straight, you only need to have it come up just in time for you to get on the brakes. So now we've established our types of fan cars, let's talk about McMurtry's specific implementation of the fan car system. Now, many earlier fan cars tried to seal off the entire volume of the underfloor. They tried to basically skirt off a large area and then suck the air out of that, generating suction. Now, this has some pretty significant problems. As a car goes around the racetrack, it will encounter different car conditions. You turn into a corner, it will try to roll. You get on the brakes, it will try to pitch down. You go over a curb or a bump, and you're going to end up with the car moving around. Now, if you try to skirt at the outer periphery of the car, the problem is that this means that every degree of pitch or roll means that you get quite a lot of translation of your skirt region. Now, if you're translating that a lot, you're going to break the seal. Full fan cars rely on a very high pressure differential, and they don't necessarily pull a huge amount of mass flow. And this means that when the gap in the skirt gets large, the car loses a heap of downforce. So what do you have to do here? Well, you have to go and spring the car up very stiffly. And you usually have to have some sort of compliant or flexible skirt that goes to the ground, and that allows you to have a little bit of more margin in terms of the sealing. And this is obviously very problematic because the stiffer we spring the car, the worse the mechanical grip of the car is. We want the car to be on the softer side to have more mechanical grip. We also have a situation where any sort of skirting that's contacting the ground is a wear item, so we'll get degraded performance over a stint. So the McMurtry take is slightly different here in terms of how they're running their skirted section in order to get performance. If you look at this shot of the front of the car, what you'll see is that there's a section in the middle of the car that clearly has a blocked off area. You can see that it's not actually that wide, but there's a small central portion of the car that must have some sort of skirt going down. Further out, you can see light through it, so there's clear air through here. We're not sealing the skirt all the way to the outside. And so what we have here is we have a much smaller section in the center of the car that is our sealed section. So instead of sealing all the way to the outside, we're sealing just the center. Now this massively reduces our roll sensitivity because we don't have such a large distance to the outside of the car. We're not going to see as big a translation in roll, and we're not going to be as susceptible to, if you were to hit a curb or something like that, it's not going to go and pop a skirt off the ground or something like that. This skirted area also doesn't go the full way forwards. It's not going all the way to the front splitter or all the way up to the rear end. So from that perspective, it's going to have less sensitivity in pitch as well. The next part of the equation is the skirt itself. Now, like I mentioned, the skirt, if you were to skirt with, say, a flexible piece of rubber, plastic, something like that, it's a bit of a wear item, and that will degrade the performance. Now, to counteract that wear, what the car has is specifically a set of ceramic sealing plates. Now, these plates are going to be very, very hard, and they're not going to wear too much when they scrape on the ground. Depending on the layout too, they may have these plates slightly sprung that might allow a little bit of compliance when they contact the ground to improve the sealing and also improve the risk of any sort of impact damage when you're going over bumps on a track. Now it's worth noting here that the McMurtry does appear to have the ability to deploy its skirt, so I think it's a fairly safe assumption here that these ceramic plates are able to slide up and down, improve their ability to conform to any sort of rough racetrack surface, and thus improve their sealing potential. In fact, with the violence at which the skirt slams down when it's deployed, I wouldn't be surprised at all if there's a pneumatic system pushing it to the ground with maybe some sort of air spring set up essentially behind it to keep those blocks forced in close contact with the ground, even if it's negotiating quite rough terrain. Obviously, I can't tell exactly how they're doing it, but if I was to design it, I would have quite a few different sections of the skirt broken up into individual sliding blocks so that the front could be at a different height to the rear, or the mid could be at a different height to the front, to allow it to move up and down over different rough surfaces and bumps. It's worth noting the type of fan they're using, which is a centripetal type blower, according to some of the images on their website. This type of fan usually gives you a little bit more of a pressure rise across it than something like an axial fan, which is what we've seen on previous cars like the Brabham, like the T50. And the trade-off for this type of fan is it can't flow quite as much mass flow. So it would mean that you'd have to seal the floor a little bit better than an axial fan design, but if you did that, you'd be able to achieve more suction from the floor and thus get a lot more downforce potential. So now we've discussed the sealing system of the car, let's talk about the fundamentals of how much suction you can get from one of these underfloors. Now, the McMurtry Spéirling has an underfloor suction plank area of around about 1 meter squared. Now, if we think of this in comparison to a conventional domestic vacuum cleaner, what are the sorts of pressures and mass flows that we'd be talking about here? Well, if the McMurtry is pulling around about 2 tons of downforce off a 1 meter squared plank area, they're pulling in the ballpark of 20 kilopascals of suction across that area. Now, most commercially available vacuum cleaners are pulling air at around about 50 to 100 cubic feet a minute, which is about 0.02 to 0.04 cubic meters a second. I found this random Philips vacuum cleaner here that pulls about 20 kPa of suction at around about those sorts of mass flow rates. Now, the McMurtry's fans use up around about 60 kilowatts of power. So if I was to say divide that into vacuum cleaners, I would have about 30 of those 2 kilowatt vacuum cleaners. Now that gives me a mass flow of about 0.88 meters cubed per second. Now why am I going through all these numbers? Well, it's because I've actually prepared a CFD model to demonstrate what's happening underneath the McMurtry when the fan turns on. Now this CFD model was actually readied back in 2022, and I just haven't had any time to do this video since I initially planned to do it back then. Speaking of things I made many years ago, it's coming up to the 4th anniversary of my race car aerodynamics course. And while the feedback has been overwhelmingly positive from the course, the primary question I've been getting is, when can we have another course? And for all those people that are looking for more, well, I'm going to be releasing a new course in July. I finally got around to making another one, and this one's going to be on flow visualization. And we'll cover everything from what ingredients to use, how to make the flow viz, how to apply it, and how to interpret it. So if you're interested in that, go to courses.jkfaero.com, add your email to the mailing list at the bottom, create an account, and there'll be an email going out to everyone on that list when the course releases, and there'll be a little bit of a launch sale to go with it as well. Now, getting back to the CFD model, basically what it is it's a shrunk version of my old Peugeot 9X8 model. So it's just that car miniaturized, and then I've gone and shoved what is roughly my interpretation of how I think McMurtry is running their plank suction setup with an area of about 1 meter squared. So basically what we have here is my old 9X8 mock-up model. So it was I basically went and just made a scaled down version of it. Now obviously when you scale down something like this, you get a lot of negative consequences where things like your wing angles and your wing curvatures will be more aggressive because you've shortened them. Your diffuser is going to be expanding at a more aggressive rate. So there's a lot of aerodynamic problems, but that wasn't really the point of this experiment. Because what I did as a main change was that I added this plank region or surfboard down the bottom down here. And what it is basically it's a cavity with 2 areas at the back that I'm going to be extracting airflow from in CFD. So I'm going to be pulling mass flow out of here at the mass flow that we calculated earlier in the vacuum cleaner comparison, and that mass flow would, in the real thing, get pulled up there, sucked up, and then pushed out the back. And then what I've got is I've got a sealing skirt around it, and you'll see all these little double lined sections are bits where I can change how much sealing there is. Then I can open them up to see what it would be like if I was to seal worse with respect to the ground. So we can see what the difference is in CFD in that if we're pulling an equal mass flow through these back bits. So why am I using vertical gaps instead of just a small gap to the ground plane? Well, small gaps to the ground plane are actually quite hard to model in CFD. You have to fit a whole bunch of mesh in there. So it's just quicker and easier for me to get a more robust model here by putting in vertical slots instead of what I would be actually modeling, which is a horizontal gap to the ground. Now this is of course a very crude CFD, and I wouldn't exactly call it a super accurate CFD, but it does show you some of what's going on with the flows, and it's a good way to illustrate what's happening. So if you can imagine, this is our model here with its little surfboard in there, and this is currently with the fan off. So I still have the majority of my conventional floor and front wing on my model, so it's making some load, some suction in the middle of the floor as a result of the rear diffuser. It's not working super great. The diffuser's not working very hard. The front wing's stalling a bit because of all the extra blockage that I've put in as a result of this central keel region. But in general, there is a small amount of suction being generated. However, when we turn the fans on, this looks quite different. You can see that in all three cases, the external performance of the floor is very similar, very unchanged. And that's really courtesy of the design that I've drawn here, which I imagine is quite similar to what they're using, which is just having this sort of rounded front, put it in the center of the car, and then have it taper back at the rear to allow you to basically have still whatever floor geometry you want on the car and run conventional aerodynamics in that region. In the years since I first prepared this model, I've thought a little bit more about it though, and figured that they've probably cut off the rear of this to not make it extend too far backwards, so that it is a little bit less sensitive to pitch and rise and fall behind the rear axle. But obviously we can see that as I've turned on the fan and I start to seal up the floor more, we're getting much more suction. So this car run was done at a speed of about 180 k's an hour in CFD, and you can see that with all the extra openings and slots that we're ending up with a suction in the floor which varies around sort of 2-3 kilopascals forward, and then we're looking a little bit higher, closer to 1 kilopascal of suction further rearwards, which isn't anywhere near the target numbers. Now there's definitely some non-physicalities going on here. I wouldn't say this CFD solution is particularly indicative of real life, but it shows you that we're not quite getting what we wanted. However, you can see that by sealing up all these gaps and going to this geometry over here with only one small hole coming in, which you could instead think of it as just having a very tight ground gap on the other areas instead, you can see that I'm able to generate much more suction. And I've actually completely saturated my scale at 5 kilopascals of suction. If I adjust that scale to 50 kilopascals of suction available, we can see that now most of my plank in this region is now sitting around about that sort of 30 kilopascal mark. So closer to the mark of where we said the vacuum cleaners would be, around that 20 kilopascal mark. And you can see that by sealing up in this region here, we're dramatically increasing our suction. And this really illustrates how critical it is that we get a good seal to the floor to maximize the suction in this region. And of course, that feeds into my earlier points about why it's hard to seal one of these floors effectively if you go to the full span of the floor. Now, like I mentioned, these runs were done at 180 k's per hour, and at that speed, the conventional aerodynamic setup was giving an SCZ or downforce coefficient of around about 1.2. I tried removing the plank as well to fix some of the mid-car aero and the front wing aero, and that brought it up to about 1.6. A good comparison point for this is my full-size 9x8 model, which was an SCZ of around about 4.9 and an SCX or drag coefficient of about 1.05 compared to the 0.81 of this new smaller model. So you can see it's not quite linear shrinking down the model because the tires make up more of the floor. You end up losing a lot more downforce by making the car narrower with conventional aerodynamics. With the light suction, so having the not quite well sealed plank, that brought the number up to about 2.6, which was a big improvement. However, going to well sealed brought it up to an equivalent of 26, which is insanely strong and demonstrates the potential in this concept. Obviously, the real world fan system sits somewhere between these two setups, but you get the idea. So now that we've covered how the fan and suction system work, let's talk about how that converts to performance on track. Now, to do that, I'm going to be making use of a simulation tool that I've shown on the channel before in the past, which is called Optimum Lap. Now, this is a very simplified vehicle physics model. It's very basic, but for the sake of illustrating the performance differences between fan aero and conventional aero, it's a useful tool. Now, this tool just considers the car as a point mass. It does not consider any suspension details, any nonlinear tire drop-offs, or anything like that. The simulation also isn't modeling any weight transfer on the car, which is an important note to make that the McMurtry with its narrower track will suffer far more lateral weight transfer than a regular car. Of course, another thing to bear in mind here is that with the fan system making most of the downforce even at low speed, the lateral weight transfer becomes a little bit less of a concern because percentage-wise, your fan is making so much downforce in the center of the car compared to the weight transfer across the car that the relative normal loadings left-right aren't as big a deal compared to if you had a low downforce or no downforce car where you get significant tire drop-off as you start to have more and more load transfer from left to right. Now, modeling a fan car like the McMurtry in Optimum Lap isn't super straightforward, so I'm going to show you how I sort of get around it. Now, I started by grabbing the drag numbers from my regular CFD numbers and basically made a basic car model with more or less constant torque until drop-off and around about 1,000 horsepower. I then did some super loose estimates of raw tire grip of around about 1.2 for mu, which is in the ballpark if we're doing a slight normal load correction for tire drop-off. Now, that was my baseline case with the fan off. But then with the fan on, what I did was I actually just played around with the coefficient of friction. So the car weighs around about a ton, the fans are adding around about 2 tons of downforce, so it's effectively equivalent of you having 3 times your regular coefficient of friction. So what I did was up the coefficient of friction to around about 3.6. Again, the nonlinearities here aren't quite correct, but this is ballpark. As a result of that, though, I had to drop off the downforce coefficient. Now, the initial downforce coefficient was back calculated from McMurtry's conventional aero numbers, which are 250 kilos of conventional aero at 150 miles per hour. Basically, it has a simple rear wing and a little bit of a front splitter on it. This would be the equivalent of around about 100 kilos of downforce at 160 kilometers per hour, or 400-ish kilos of downforce at 320 kilometers per hour. Now, that gave me my initial number of 0.84. However, when I multiply the coefficient of friction by 3, I have to drop the downforce coefficient by a factor of 3 to correct it back into the real world. So that's what I've done there to get that car model. Both these cars are done with 2-wheel drive. Now, for a comparison model that we can compare this car to, I put on a conventional car model as well. So this conventional car model would have the exact same specs as the fanless one, but I increased the downforce and drag coefficients to what I consider quite easily achievable numbers for a car of this style. Of course, considering that if I did conventional aero, I'd make the car a little bit bigger than how small the McMurtry is. So I went to drag coefficient of 1.4 and downforce coefficient of 10, so that's your SCX and SCZ. This is what the downforce plot for the SCZ10 that this car is configured with looks like, and you can see down here is the line for 2 tons. So you can see at about 200 k's an hour, that's when we'd be hitting McMurtry levels of downforce. All other aspects of the car are treated as the same, which is obviously not 100% correct because obviously the fan and skirt system add weight, there's a few things going on there. There's also a difference here with the narrower car of the McMurtry can take a slightly different line choice, particularly on tight tracks, and that gets you a lot more lap time on those particular tracks, whereas a wider car can't take it, but we're going to just ignore those things so that we can have a look at the overall picture. Now, the first thing I've done is simulate the performance of the cars around Monaco, which is of course a low-speed circuit. Now, what we can see here is the McMurtry with no fan in orange, our conventional aero car in the blue, and the McMurtry in purple. And you can see that particularly in the low speed corners, we have a huge advantage on the McMurtry. In the higher speed stuff, the gap closes a little bit to the conventional aero, but in general, the McMurtry is just faster, and realistically, it's faster at all points of track. You can also see how big the delta is versus the non-fan car, because the non-fan McMurtry just doesn't make that much downforce. And you can see that it makes a pretty mega difference to just go to a conventional aero, but then obviously the fan makes a much bigger difference again. At a circuit like Monaco, the drag doesn't matter as much, so our conventional aero car doesn't have too much of a deficit in terms of the trajectory of its straight line speed. Obviously it enters the straight slower, so it finishes the straight slower, but the overall acceleration in the top end isn't really hitting us too hard. What if we instead go to a circuit like Silverstone? Well, this is what happens here. And you'll see that the story is a little bit different. Again, the McMurtry with the fan on is significantly faster than the McMurtry with the fan off, that's no surprise. But the higher speed nature of Silverstone actually brings in a few corners where the conventional aeroed car is doing a little bit better. Now, of course, the track model here isn't perfect, but you can see there's just a few high speed corners where our conventional aero car is making a little bit more downforce, and that's allowing us to get through those corners at a higher apex speed than the McMurtry with a fan on. Of course, the McMurtry is still miles faster. We're talking a 13-second pace differential between the two cars, and then there's another 30 or 40 seconds back to the McMurtry with the fan off. But the gap is much closer than at Monaco, where the gap was more like 30 seconds between the conventional aero and the McMurtry with its fan on. But this comparison isn't really a fair fight, because the reality is that if we were doing a car of this nature, we wouldn't be limiting ourselves to just having a static conventional aero car. We would almost certainly be using an active aero car to compete in this sort of space. Now, with active aero, you get the benefits of reducing the drag on the straight whilst maintaining the downforce at lower speeds. And that would solve a lot of the issues we're seeing on this Silverstone lap, where the McMurtry has a much higher top speed because its drag is just much lower. And I believe that's pretty accurate to the real world because it's got smaller wings than a heavily winged car. And of course, the fan system is going to backfill some of the wake of the car when you're going along, which is going to reduce the drag as well. It's also a much smaller car with a much smaller frontal area, and that will assist with keeping the drag low. Of course, once we bring active aero into the equation, this is going to look very different. So I've simulated a car with active aero on it. And to do this, all I've done is I've just essentially kept the downforce coefficient high because we're going to keep that high in any sort of corner where we would need downforce. We'd have the active aero closed. But I've reduced the drag coefficient down to 0.9. It's still higher than McMurtry because I'm going to say that my active aero car is a full-size, full-width car, just with active aero. So the McMurtry with its smaller frontal area would be less draggy. But I think these are quite believable values. What we can see around Silverstone is that we significantly improve that top speed end of the performance window once we have the active aerodynamics on. You can see in some areas we aren't getting quite as much acceleration at the top end, but in general this is enhancing the performance a lot. So going to active aero here has saved us around about 4 seconds a lap. We're still 9 seconds off the McMurtry, but we're getting closer. There are some fallacies here though, where because I've used a low drag coefficient at where we will want high downforce, you can see that right here we end up with continually high acceleration through something that's obviously a high speed corner where the McMurtry has to slow. In reality, the active aero would be closed, so this curve would flatten out a lot more. And that's not even to mention the energy you'd be putting into the tires through the corner, which would slow you down again. But the McMurtry is still faster at all points on track. And that super doesn't make sense because the McMurtry did lap Silverstone, but it only pulled around about a 1 minute 40 lap time. Now this lap time was done at 80% power and 80% downforce. And this is something we can easily simulate. And what we can do is we can compare it to a car that was much faster around Silverstone with conventional aero, which is of course a car that I'm quite familiar with, the Mercedes W11. If we go through and overlay the W11 and the McMurtry at 80% power, 80% downforce onto this plot, we can see a few things. Firstly, the McMurtry at 80% power, 80% downforce loses around about 7 seconds versus being at full power, full downforce. So it's safe to say that McMurtry lap time would actually be more around the 1 minute 30 mark, maybe 1 minute 33, if it had full power going. That's still 10 seconds behind the W11 in real life. Now in this simulation with W11 numbers, the W11 is only about 6/10 faster than the McMurtry versus the around about 9-10 seconds that it would be faster in real life based on those other numbers. So obviously there's a few assumptions I've made that are incorrect around the McMurtry's pace, and the McMurtry's fan pace is being over-rewarded in the simulation. But even with that in mind, we can still just have a look at where the McMurtry makes its speed compared to the W11. In lower speed corners, the McMurtry is significantly faster. You can see here that the orange line is the McMurtry with the 80% fan, 80% power, versus the green line, which is the W11. Now you can see in the lower speed corners, the W11 is still significantly slower than the McMurtry, even at 80% fan. But then in the higher speed content, the W11 is significantly faster through sort of your Maggots, Beckett's, stuff like that. It's a much quicker car. And a lot of that is going to come down to the reduced mass of the car. It's obviously got conventional downforce plus a very light mass plus a good chunk of power. And you can see that makes it really fast under brakes when you initially get on the high speed braking efforts, and it makes it really fast through the higher speed corners. So let's explore that if we were using just conventional aerodynamics and keeping my McMurtry as the base model, what would we have to do to beat it in my simulation? How can we beat this car with conventional aerodynamics, still with the same sort of ballpark weight and constant tire properties? Well, to test that question, I've got a more extreme version of my aero car prepared. Basically what I've done is up the downforce coefficient to 14 for SCZ. Now that is high, but I assure you it is definitely not impossible. Now this is what that downforce plot looks like for that more extreme SCZ of 14, and you can see we're hitting that 2-ton mark around about sort of 175 kilometers per hour mark. Now on top of that, I've got two other variants. One is looking at using that additional mass that we've saved by not running the fan and skirt system and instead putting it into a frontal motor and all-wheel drive. The mass would be about equivalent to achieve this. And this is just going to be the exact same properties as my Extreme Aero version, just with all-wheel drive. We've then got an alternative, which is instead of using that mass for all-wheel drive, we use it to make the car two-wheel drive and just do the mass reduction. So on that one, I've taken off 200 kilos off the car, which in fairness is probably an overestimate, but still going to be an interesting thing to see the effects. Now this is all my Active Aero Extreme configurations overlaid onto the McMurtry's lap at Silverstone, and all of them exhibit a faster lap time than the McMurtry. Of course, I don't fully believe this result though, because if we have a look, it's basically taking the entire back section of the circuit completely flat. So I don't think that that's a realistic indication. So I'm going to just quickly switch to Spa instead. Now, looking at the results on Spa, a few things become apparent. Firstly, the McMurtry is still incredibly quick. The conventional Active Aero gets beaten by it by around about 11 seconds. The Extreme Active Aero still gets beaten by about 2 seconds. But the all-wheel drive Active Aero just pips it with 0.15 of a second improvement. And then the Extreme Lightweight Aero is way quicker at 8 seconds faster. Now, if you have a look, there's a few things going on where that pace is being found. Firstly, the conventional Aero cases seem to do a little bit better through Eau Rouge than the McMurtry. And then some of the higher speed content out the back, the conventional stuff does a lot better, particularly the lightweight version, which is doing much better in all the high-speed stuff. And obviously all the conventional designs do much better at high-speed braking than the McMurtry, where they're making a lot more downforce. The McMurtry is still very fast in the lower speed content, but Spa just doesn't have that much lower speed content. There's basically the last chicane and the first corner. Those two things the McMurtry is smashing everyone else in, but at the other points on the track where it's higher speed, the McMurtry just isn't there. Factor into this that a lighter car would in fact have better tire grip because it would have better normal load sensitivity. Then I think it would be the sort of thing where a conventional aero car would still be able to beat the McMurtry on these higher speed tracks. Just closing the loop and going back to Monaco, it's worth noting the McMurtry is still hilariously faster there, with around about a 12-second improvement to even the fastest config that I have, which is the Active Aero Extreme Lightweight. So it would still be a very tall order for any of these conventional cars to beat the McMurtry on a lower speed track. It's worth noting too that drivability comes into the equation as well, particularly if you have an amateur driver, where the McMurtry's consistency in downforce and consistency in grip is going to make it much easier for an amateur to be able to drive this car. Whereas conventional downforce cars have their downforce vary with speed, and this inherently makes it difficult to drive because different corners have to be taken at different target grips. Different speeds require different braking forces to achieve the ultimate lap time. In my mind, I think the optimum for a lot of tracks actually lies halfway between these cars, where you have a conventional aero car with an active aero system, and then a light fan assist, something to just boost those aerodynamics on your conventional car, help a bit with the low speed corners, but still have excellent performance in the high speed. It's worth noting too that conventional cars are always going to be less sensitive to ground and track surface issues than the McMurtry is going to be. Because fundamentally, the McMurtry has a platform that is dependent on contact with the ground. And as much as it can try and absorb variations in the ground, I think it's going to struggle a lot to set fast times on rougher tracks like, say, the Nordschleife, where the bumpiness there requires you to have a high ride height on a conventional aero car. So I don't see how a ground skirt is going to go particularly well there. And that brings us to the final point of discussion, which is active suspension on fan cars. Now, when the McMurtry first launched and did some of its Goodwood stuff, in a lot of the documentation there was discussion of active suspension systems on the car. Now, since then I've tried to look up these details on the car, but there's no real mention of them anymore. It makes me wonder if they've switched to a conventional suspension system. Either way, let's discuss it as if they had to run an active suspension system. Now, active suspension systems are very good at being able to control ride height, and that's super useful for both a fan car and a conventional car. But they are not without their own sources of issues. The first one is that an active suspension system requires a certain amount of energy to operate in order to maintain a consistent ride height. You have to work against the downforce on the car. Now, if you're making 3 tons of downforce all the time, you have to have an actuator that's constantly pushing up and down effectively 3 tons of downforce. This creates a lot of energy, which you have to draw from somewhere, in this case, the battery on the car. Being an electric car, this is going to reduce your potential for power output and reduce your potential for going for a long time on track. In addition to that, these actuators can be quite bulky and heavy. Now, in an active suspension system, you need the response rate to be very quick. When you do that, you end up with a pretty tanky actuator, which can be quite heavy. So these systems come with a weight penalty as well. But finally, I just want to talk about the fact that an active suspension system is not without compromises in terms of spring rate. If we look at the McMurtry going around on track when, say, it did its Top Gear record, you can see the car looks incredibly stiffly sprung. Now, that makes perfect sense given the nature of its system. Whether it be conventional or active, it would effectively have to have a very high spring rate. And this is what I want to talk about with active suspension. Everyone seems to think that you can just control the ride height of a car with no consequences. But there's only one way that you can actually stop a car moving around a whole bunch, and that's by effectively increasing the spring stiffness. If you hit the brakes and the front of the car wants to go down, say, 20 millimeters at your desired conventional spring rate, and you want it to only go down 2 millimeters to try and hold better platform control, well, the only way you can achieve that is by effectively instantaneously stiffening the front end. You're basically fighting the weight transfer onto the front with the actuator, but the only way you can do that is by shifting the weight transfer onto the front faster. Now, this will inevitably lead to less grip than having a system that allows the front to dive a little bit because you are just increasing the stiffness. So while you can help keep your platform nice and level, which is obviously excellent for aero grip, and in many cases, the improved aero grip can outweigh any consequences of the increased effective spring rate, it's not like your springs are magically softer. You are adding an artificially high and stiff spring rate through the use of an actuator. By no means am I saying that active suspension isn't a good thing. I would always want active suspension on my car if it had no other compromises. But I think some people think of it a little bit too much like a magic bullet and don't realize that there are consequences to it being fitted to a car. Anyway, I hope this has been a very interesting breakdown for you of the different aspects of the car and why it's so fast. I personally find this a super interesting car. I really loved it when it came out. The pace of it at low speed is just absolutely mind-boggling, and it's so cool that someone actually finally did this and is doing all the cool demos like driving upside down. So props to McMurtry for pulling all this off. Well, that's all for this video analysis. Thanks for watching. If you enjoyed it, don't forget to hit that like button and subscribe to my channel for more content like this. Leave a comment below on what videos you'd like to see next from me, and hopefully, I'll see you next time.